In this problem, we're asked to look at a rectangular bar, rectangular cross-section, which is acted upon by an axial force P and a bending moment of M. We also have information here that if we look at the point A on this bar, if we look at the state of stress, we rotate that stress element through 30 degrees in the clockwise sense, what we end up with are the components of stress that are shown. So the information that we have is sort of a mixed bag here of stuff. We know the bending moment M, but we don't know P. On the other hand, if we look at the components of stress, we have sigma x prime and we have sigma y prime, but we don't know what tau x prime y prime is. So let's consider first what we have for over here on the beam. If I look at the state of stress at A, and if I don't rotate that stress element, I just keep it aligned with x and y, like this. The components of stress that I have are simply sigma x. This tells us that the sigma x is going to be the principal stress of sigma p2. The sigma y is equal to a 0, so that's our sigma p1. And then our tau xy, there's no shear stress that we see in that phase, and that's equal to a 0. So that's one piece of information that we get from looking at the loading that's acting on that beam. The other part of this is that if we look at the normal stress, it's going to be made up of two parts. So it's a combined state of stress. The components are very basic. We have a bending, I should say a flexural stress, which is going to be the minus my over I. We'll define those terms and give as many numbers there as we can in just a bit. And we add on an axial component stress, which is constant across the cross section. So that's given by P over A. What this means is that at point A, we have that the normal component stress is minus my over I plus P over A. And now we'll give the numbers. It's given up there that the bending moment M is equal to 2,000 Newton meters. We can see here that the Y there for point A is 0.05 meters. The cross-sectional area is just the B times the H, so that's 0.03 times 0.1. And the second area moment is 1/12. B, which is 0.03, times H cubed, so that's 0.1 cubed. So you can do the numbers there to calculate out A and I. What I want to do is move on to the stress distribution. The stress transformation. Because what we want to do is to be able to relate the known components of stress here to what we know best in terms of P and M for this. So we know that sigma x prime, reading that from the picture, is a minus 15. Sigma y prime, reading that from the given information, is a minus 0.5. And the shear stress at that rotated state, we don't know. But what we can get from this is that sigma average, which is sigma x prime plus sigma y prime divided by 2, that ends up being a minus 10. And the second parameter that we need for a stress transformation, which is R, that's sigma x prime minus sigma y prime divided by 2 squared plus tau x prime y prime squared, like this. So if we want to write this out, that's going to be a 25 plus tau x prime y prime squared. So therefore, what we have here is that we know that sigma x, we know is equal to the first principal stress. Our equations from before are sigma average plus R and sigma y, which is sigma P2, which is sigma average minus R, is given by that. So sigma x, we know from what we've seen before, is equal to P over A minus my over I, and that sigma y is equal to a 0. We know sigma average. We don't know R. R involves this. So what if we would add these two equations together? We would get here that sigma average times 2, then the R minus R will cancel out, is equal to P over A minus my over I. And then it's a simple matter of taking this. We know that sigma average was equal to minus 10 and all the other stuff there. We can see here that P is given by this. So really the basic idea here is that by looking at the physical loading on the beam, we know the orientation of our principal axes, X and Y. On the right-hand side, our stress components when the element is rotated, we know 2 out of 3 of those. We combine all that information together with the stress transformation equations, Moore's circle, and we're able to back calculate what that axial component of the load there, P, is.